you very much, Aditi and Rita, and thank you everyone for joining. It's a pleasure to join the Landscape Live seminar series. It's a great service to the community, and I've enjoyed many of the talks so far. So today, I'm gonna be talking about some of the work that I've been doing over the past decade or so. And in general, my work is I use engineering tools and tools from applied mathematics to describe the evolution of coastal landscapes. Here you see a few examples. On the left, you see a Fluvio-deltaic environment / continental shelf under glacial cycles. Here you see in the center a barrier island migrating towards land over thousands of years. And here on the right, I'm still not sure what the one on the right is. So if anyone has some ideas, maybe we can chat afterwards. But what all of them have in common is that is what we call a moving boundary approach. And the idea is that we track the key geomorphic boundaries, like the shoreline, for example, to describe the evolution of these landscapes. In addition to that, what these simulations have in common is that they combine an idealized geometry with sediment conservation, with mass balance. Okay, so that's what I'm going to be talking about today. And of course, this is the product of effort from a number of students and collaborators listed here, and I will mention some of the students throughout the presentation. But now let me step back and just talk in general about what my group is interested in. So we are interested in the evolution of coastal environments over a wide range of spatial and temporal scales, all the way from continental shelves, fluvial deltas, which will be the topic of the first part of this talk, to barrier islands and developed barrier islands like the ones in Virginia. You see here in parentheses the rates of landward migration. So some of them in Virginia, like Cedar Island, I will show later, have been recently migrating at rates of 10 meters per year, exceeding 10 meters per year on average. So, and that is in contrast with developed barrier islands like Long Beach Island and some others in New Jersey and some other areas in the along the coast of the United States and some other areas around the world. They are heavily developed and they have been fixed in place. So that the relative effect of human activities, human coastal engineering on how these landscapes evolve is of interest to us. And something that I won't talk about in this presentation is also the fact that we are actually interested in the interplay between physical and biological processes. There is a student of mine, for example, interested in the role of net evaporation rates on mangrove island morphology. Some other student in the past has looked at ridge and swell systems. And in general, if you are interested in any the evolution of coastal environments, feel free to reach out. And I would be happy to talk about any coastal environment. But why do we care first? Coastal environments have been places for civilization over millennia. Think about Egypt, the Nile deltas. I mean, there are a number of examples, but even today in the United States, 40% of the coastal counties are coastal. And that means that they provide a wide range of ecosystem services, including flood protection and groundwater and hydrocarbon reserves. Think about Louisiana, for example, or Texas, right? But at the same time that they are often heavily populated, and they provide so many important ecosystem services, they are also vulnerable to sea level rise and climate forcing. And in particular, low-lying environments like barrier islands and fluvial delta. So here there are a couple of examples on the left. On the top, you see Matalonkin Barrier Island in New Jersey before and after Hurricane Sandy. So they can, this particular storm created a lot of damage along the northeast in the United States, and there are many other examples like this. In the case of fluvial, in the case of the Mississippi Delta, you see here in red the area that has been lost between 1932 and 2010. So basically, it's like a football every hour if you do the calculation. So, and when you lose so much area of marsh along the coast, then populated centers like New Orleans are going to be more exposed to future storms, right? And that became clear during Hurricane in 2005, right? With Katrina. So that's why there are a number of restoration projects on the table that are looking at opening the Mississippi River on different locations, create some diversions that create some natural buffers to protect populated centers like New Orleans. But another reason why coastal environments are very important is because they store valuable information about paleo sea level and paleo environmental conditions about the past, right? So if you look at, and this is an experiment that I'm going to be showing later, but this Flume experiment you see in plan view here is a sedimentary, the sedimentary prism with the channels avulsing and migrating, and this is the silhouette curve. If you look at the stratigraphic section or a couple of stratigraphic sections like these two, can you tell what the sea level curve this sedimentary basin experienced? And it's not easy. It's a difficult question to answer, even though it's easy to pose, right? So we will talk about that later too. So in terms of modeling approach, in order to understand the evolution of coastal landscapes in a process-based way, we have to go with whatever it takes, because it's not an easy problem, right? So we go with mathematical modeling, geomorphic and stratigraphic experiments, and field observations, right? And today, my presentation is going to be centered around mathematical modeling, which is the core of my research. But we are interested in the connections with Flume experiments and field data, in particular with, I'm not gonna be talking about some of the field data that we collect. This is one of our drones, but I would be happy to talk about that later. So in terms of mathematical modeling, as I mentioned before, in our group, we are interested in all mathematical modeling complexities, but we often find ourselves developing simple models like the one here, looking at a barrier island migrating towards land. And the key ingredients of this type of moving boundary approach is an idealized geometry and sediment conservation, right? So what I'm going to do now is to go over a couple, three examples of how to apply this moving boundary approach over a range of time scales. So I'm going to be looking at the Fluvio-deltaic environments / continental shelves over glacial cycles, then barrier islands over millennia, and then I'm going to be talking about timescales in the order of years to centuries, in which the role of human activities and coastal engineering plays a role. So let's start with part one. And the idea is I'm going to discuss a moving boundary framework that in this case is built around this driving question here. Do the dynamics of the fluvial surface play a role in paleo sea level reconstructions? Okay. Now, a little bit of context. If you are reconstructing sea level over timescales of in the order of glacial cycles, millions of years or hundreds of thousands of years, the most common approach is sequence stratigraphy. And sequence stratigraphy, just I include here a few sketches to that hopefully illustrate briefly what it's about. But the idea is that if you have low sediment supply from land, respect to the rate of sea level rise, then what you're going to see is shoreline retreat, right? So that's why the shoreline initially in this sketch was here, and then it's here at a later time, right? In the case of high sediment supply, respect to the rate of sea level rise, what you have is shoreline advance towards the sea, or shoreline regression, right? You have regression, and that's why the shoreline in this case moves seawards. And if the two of them, sediment supply and rate of sea level rise, are balanced, then the shoreline stays in place. But in all these cases, if you notice, because you have sea level rise, you have sediment, you have a gradation along the river network here, right? You have the fluvial surface is basically responding instantaneously to these changes in sea level. That is one of the assumptions of sequence stratigraphy, right? So that is what we are going to question with a moving boundary framework now. And there are a number of assumptions also in sequence stratigraphy, other internal processes that sequence stratigraphy doesn't account for. Even though it's a good first step, we need to learn more about some other factors. I'm not going to be talking about these other ones, but those are also of interest in my group. So let's focus on the dynamics of the fluvial surface. So, and we develop a moving boundary framework to address this question. And the first step is to define the idealized geometry. So the idealized geometry in this case is a linear basement like this one, on top of which you have sediment and water inputs coming from upstream. And those sediments are going to deposit, forming a sedimentary prism like the one that you see here, right? The fluvial surface in this sedimentary prism is delimited by the alluvial bedrock transition and the shoreline. Those are the two key geomorphic boundaries. So the trajectories of these geomorphic boundaries over time are going to describe the evolution of the sedimentary prism. So now the next step after selecting the idealized geometry is to select the sediment transport formulation that we want to use, which in this case we assume that it's a simple relationship between sediment flux and the local slope, and combine that with a one-dimensional sediment balance. Okay, so when you do that, when you combine those two, you get the so-called linear diffusion equation. Okay, but in this case, instead of the parameter here is the fluvial diffusivity, right? This equation is used in many other fields, but in this case is specific to the evolution of fluvial delta. So H in this case is the elevation of the fluvial surface at any location, and T is time, X is the location along this profile, right? Now, what is interesting from the mathematical point of view of this framework is that the boundaries that delimit the fluvial surface, the alluvial bedrock transition and the shoreline, they are moving over time. That's why you have R is the location of the alluvial basement transition, S is the location of the shoreline. They are a function of time. And because of that, instead of requiring only two boundary conditions, we require 4. 2 additional ones per moving boundary. And that is where the connection with heat transfer comes into play. So this is something that John Svensson in 2000 with Von Wohler and Chris Paula came connected, right? So there is a problem in physics called the Stefan problem, which is basically a chunk of ice that when you apply a heat source is going to melt. And the interface between water and ice is a moving boundary. And it's a moving boundary that is going to move to the right. It's called the melting front. It's going to advance to the right. Well, it's going to advance when you provide the latent heat of fusion, right? Similarly, in the case of fluvial deltas, we don't have a heat source, but we have sediment supply. And we don't have latent heat, but we have ocean depth. So when the sediments that reach the shoreline feel the depth, ocean depth, then the shoreline will advance, right? So what we did with William Anderson, one student in my group, what we did is to extend this modeling framework to be able to account for patterns of erosion and deposition along the fluvial surface, as opposed to only aggradation, right? And that allows us to look at cycles in shoreline regression and transgression, cycles in shoreline advance towards the sea and retreat towards land, right? And something that I'm not going to be talking about today, at least in these three parts, I will show a video at the end. We are also playing with more complex sediment transport formulations that account for the threshold of motion, right, SC. But let's look at some simulations, right? So that's enough equations for now. So what I'm going to do is to now, with that modeling framework, show you a few examples under fixed sea level, constant sea level rise, constant sea level fall, and sea level cycles. And sea level cycles is going to be the most interesting one, right? So just quickly, for those that are not very familiar with the stratigraphic terms, so if you have the alluvial basement transition migrating towards the sea, you have what is called coastal offlap, and you have incision, degradation of the top set, right? And as in contrast, if you have the coastal, if you have the alluvial basement transition migrating towards land, you have coastal onlap and you have topset degradation, right? And in the case of shoreline, the shoreline, if it's you have regression if it's migrating towards the sea, and you have transgression if it's migrating towards land. Okay. Now let's start with a constant sediment supply and fixed sea level. So in this case, you see here on the left, you see the trajectories of the alluvial basement transition and the shoreline. Both of them, as you can see, are advancing in opposite directions, and the rate of migration decreases over time. And the reason is because you have constant sediment supply. So it's as the delta grows in size, it becomes more. It would require more sediments to maintain the same rate of shoreline advance, right? So it's not surprising that under constant sediment supply, if the area of the sedimentary prism is increasing linearly with time, then any dimension of the sedimentary prism, including the trajectories, is going to follow the square root of time, right? So there is an analytical solution, a closed solution for this set of equations that I presented before. So let's test it against some flume experiments. And these experiments were carried out at Nagasaki University, and Tetsuji Muto and Wonsaki, they mentioned that these were the most boring experiments that they ever run, but they serve the purpose because we could show that the model, despite the simplicity of the sediment transport formation, etc., was actually able to describe the trajectory of both the alluvial basement transition and the shoreline. So you have here the solid line, the lines are the numerical results, and the circles are the results from the flume experiments. And there were a number of model runs, not only this one. This is just for as an example, right? So then we can go into more complex scenarios. Constant sea level rise. Under constant sea level rise, initially you also have the shoreline and the alluvial basement transition migrating in opposite directions, but eventually the geometry of the sedimentary prism breaks, and the shoreline and the alluvial basement transition migrate towards land at the same pace. And this also was validated against flume experiments by Tetsuji Muto and Gary Parker. What happens under sea level fall? Under sea level fall, you also initially, as you see hopefully in this simulation in a moment, you're going to see the alluvial basement transition and the shoreline migrating in opposite directions, but eventually sea level fall forces both of them to migrate towards the sea and it forces degradation of the top set. And this was also validated against flume experiments. Here you see the white arrow at different points of the experiment, 30 seconds, 450 seconds, etc. Initially, the alluvial basement transition migrates towards land and then retreats or reverses the direction and migrates towards the sea, right? All right. So far, these scenarios, fixed sea level, constant sea level rise, constant sea level fall, yeah, we can use this moving modeling framework, but the truth is that we don't need a very complex fluvial surface. Even with a straight line, you could actually reproduce the dynamics, even if it's not, you know, too very precisely in terms of the rate of migration. You can reproduce with a linear top set as in a scenario in which the alluvial basement transition and the shoreline are migrating in opposite directions, or in a scenario in which they are migrating towards land, or in a scenario in which they are migrating towards the sea, because in all those cases, you have the top set either aggrading or degrading. But what about the scenarios in which the fluvial surface both degrades and aggrades? There is both erosion and aggradation at the same time. And that is what happens under sea level cycles, right? So under sea level cycles, what you are looking at here is a simulation describing the evolution of the sedimentary prism under sea level cycles. The sea level cycle, the sea level curve is shown here in the upper right. And you hopefully can see the change in colors, that you can imagine those as age, right? Because it basically represents the time of deposition of each of the sediment layers. The light blue, the dark blue, for example, was the first one to deposit. That's why here is in the interior, right? And I want to mention two things about this this simulation. The first thing is notice the changes in the relief and the curvature of the fluvial surface, right? So you have here under sea level fall, concave down, and a steep profile, and the sea level rise, you are accumulating much more sediments during sea level rise in the near shore portion that flattens the profile. And during sea level fall, you actually bypass a lot of sediments to build the delta front. Okay. The second thing that I want to mention here, apart from how important these changes in relief and curvature of the fluvial surface are, is that the upper portion of the fluvial surface is actually out of sync respect to what is happening in the sea level at the boundary condition, right? What means is that during sea level rise, you can actually have erosion in the upper portion of the fluvial surface. And those lags mean that you can have river incision during sea level rise. So some of the stratigraphic indicators of the upper portion of the Fluvio-deltaic surface might not be good in the indicators of contemporaneous sea level changes. Right? So, but this is maybe a more detailed way to describe when that happens. This is the trajectory plots. So the yellow and the purple show the trajectory, the trajectories of the shoreline and the alluvial basement transition under fixed sea level. And under sea level cycles, you have the trajectories in blue of the shoreline and in red of the alluvial basement transition. Okay, and these are the sea level cycles in the dashed line, right? So in gray, what you can see is periods of time during this simulation in which you had erosion in the upper portion of the fluvial surface during the sea level rise phase. So you could actually have, again, the erosional features, the formation of a river terrace in the upper portion of the fluvial surface during the sea level rise phase, right? Here there are just a profile that shows that this dashed line erodes to the black solid line in the next time step. So you have erosion in the upper portion of the fluvial surface and deposition in the near shore, right? But this is just a theoretical result. We wanted to find a way to validate this against field data or flume experiments. I will be very much interested in discussing with you about ways to validate this in the field, but we started with flume experiments and a set of experiments from Tulane University. Just here, the plan view of the sedimentary deposit and the channels. And this sedimentary deposit was exposed to this sea level curve shown in panel B. And even though we analyzed the entire experiment, I'm going to focus in this presentation only in the period here under high amplitude sea level oscillations. And to address this specific question, right, that I mentioned earlier, do the dynamics of the fluvial surface matter when in paleo sea level reconstruction? So to answer that question, we look at a location in the upper portion of the fluvial surface and a location near shore, and look at the changes in the elevation of, over time and see how do they relate to the changes in sea level. So we basically take the radial average because we want to remove the effect of river avulsions and migration of rivers. What we're interested in is, on average, this profile is responding instantaneously to sea level variations, or is there a lag, right? And here is the result. So here is the key point of this part one. In the black solid line is the sea level, and the light gray here is the near shore location. Hopefully you can see that the near shore location is following quite well what the sea level is doing. So what that means is that the near shore location is responding instantaneously to those changes in sea level. However, the upstream location is completely out of sync. And here with an eye, I'm showing the periods in which you actually have incision, erosion in the upper portion in that location during sea level rise. And it happens a number of times throughout the experiment, right? So this supports what we were showing in the theory. Now let's go one step further. Why does this happen? Let's estimate, let's quantify the changes in the relief and the curvature of the profile in this flume experiment. So the slope is, the average slope is EC. And as you can see, it's also following the sea level variations. Is getting milder, getting steeper, sorry, during sea level fall, and it's getting milder during sea level rise, and on and on and on. It's basically following the same pattern. Now, for the curvature, we have a proxy for the curvature that is called delta. How do we define the delta? It's just the area difference respect to the linear topset, the area in green, divided by the length. So you can imagine this as basically the deviation, the average deviation that this profile has respect to the linear case. And if it's positive, it's convex, like the one here. And if it's negative, it's concave, like the one here. And as you can see, this proxy for curvature is actually following sea level oscillations quite nicely. So the mechanism in this experiment, even though subtle, because look at the magnitude of these changes, is in the order of a few millimeters. So if you are looking at the experiment, you wouldn't notice these changes in the curvature and relief, because there are so many other things happening, right? The rivers are avulsing, meandering, and that is going to be on top of these subtle changes. But these changes result in a lag in the response of the upper portion of the fluvial surface. And let's go one step further. What are the patterns of sedimentation and erosion? So what I show here is the pattern of the cumulative sedimentation pattern over the sea level rise phases. And here is the cumulative sedimentation pattern over the sea level fall phases. And basically, what is going on here is that this pattern of erosion with the minimum sedimentation rate in the center of the profile is shifting the profile from concave at the end of the sea level fall phase to convex, which is what you typically have during sea level rise phases, and the opposite during sea level fall, right? You are transitioning the profile from convex at the end of the sea level rise phase to concave by depositing most of the sediments in the center of the profile, right? All right, so that part one basically is hopefully illustrates that we have to be cautious when we are looking at stratigraphic indicators of the upper portion of the fluvial surface. Those stratigraphic indicators, like a river terrace, is often associated with sea level fall, but we have to be cautious, right? Because it could actually still be the result of there might be some lags, and it could be associated with the sea level rise phase. Now let's talk about barrier island migration over thousands of years and barrier shelf deposits. Okay, so barriers are arguably among the most dynamic systems in the world. Here there is an example of Cedar Island. This is Cedar Island in 1984, and the shoreline at this point in time is in red, and this is the same barrier island in 2016. So the barrier has rolled over a few times over itself, and on average, this barrier island has migrated towards land at 10 meters per year. So as barriers migrate towards land like this over thousands of years, they can leave sediments behind, barrier self-deposits. And often these barrier self-deposits are associated with sudden changes in external forcing, like, for example, pulse in the rate of sea level rise. So Dan was interested in this problem, and he looked at a number of papers looking at barrier self-deposits, and he found that there was a characteristic spacing between barrier self-deposits. So if you are in the English Channel, this characteristic spacing was in the order of 2 kilometers. In the case of Florida, it was in the order of 7 kilometers, suggesting that there might be some other mechanism that could actually be behind this periodic deposition of barriers. So to address this question, Dan used an existing model that assume an idealized geometry as shown here that has a linear surface. It characterizes the superior portion of the barrier with two parameters, the average elevation respect to sea level and the width. And the key geomorphic boundaries are the surface toe, the shoreline, and the back barrier face. So the migration, the change of this, the location of each of these geomorphic boundaries can be then described as a function of the key processes: rate of sea level rise, overwash, fluxes, which is basically the process that brings sediments from the front of the barrier to the top and the back, and allows the barrier to migrate in a conveyor belt fashion towards land and keep pace with sea level, right? But also, the exchange of sediments between the upper and the lower surface, right? Via wave sediment transport. So those are the processes in this simple framework, right? So now the question that we are addressing is this one. And with this simple model, what we found is that actually it can describe a number of different barrier island behaviors. We can have high drowning when the overwash fluxes are not large enough to for the barrier to keep pace with sea level. It's basically almost going to lead to passive drowning almost of the barrier, right? But even if cases in which the overwash fluxes are large enough, the barrier might actually still drown via with drowning because the surface doesn't respond fast enough, doesn't send
sediments from the lower surface to the upper surface fast enough to maintain the geometry during this landward migration. And then dynamic equilibrium is when they both overwash and surface response are balanced, and the barrier basically migrates towards land and maintains the geometry and doesn't leave any sediments behind. This is what was commonly assumed, right, that barriers would do over thousands of years, cannibalizing themselves completely, right? But what we found with this, also with this model, is that you can actually have alternations of rapid landward migration towards land and aggradation despite having constant forcing, despite having constant sea level rise, right? Why? It's because overwash is basically eroding sediments mostly from the upper surface, flattening the surface as the barrier migrates towards land. If the surface doesn't send sediments from the lower surface to the upper surface fast enough, there is going to be a lag that results in this alternation of rapid migration and aggradation, and also alternation of erosional surfaces, ravine surfaces, and barrier sediment deposition, right? So Dan found that this can explain some of the observations of the characteristic spacing between barrier self-deposits, as well as the volume deposited in different locations around the world. So here in New Jersey, Florida, Long Island, English Channel, South Africa, Italy. So in general, there are this depends on the volume, and the characteristic spacing depends on a number of factors, but one of the key ones was the steepness of the shelf. So if you have a steep shelf, the characteristic spacing is going to be small, and the volume deposit is going to be small as well, as opposed to a mild shelf where you're going to have larger volumes of barrier self-deposits and a larger characteristic spacing. So what is the key message? Well, that barrier self-deposits can be actually quite large in a mild shelf, and not necessarily associated with a change in external forcing. So we have to be cautious associating barrier self-deposits with a pulse in the rate of sea level rise, for example. Right. All right. Now, part 3 of the talk, and I'm just gonna go over this a little bit faster. Here, what you see, we are talking about years to centuries, right? So the role of humans, the role of development and human activities becomes important. Here, as an example, you see an engineered dune in Long Beach Island. This dune is 7 meters tall, more than 21 feet high, right? These are massive features that are going to play a role on the way that these systems respond over these time scales, right? So as I mentioned before, undeveloped barrier islands are very dynamic features, right? And this is the example of Cedar Island, but in contrast, you have some places along the East Coast, or in particular in New Jersey, like Seaside Heights, and that have been fixed in place for several decades because they are heavily developed. And how do they do that? How do they fix those landscapes in place? Through coastal engineering, like hard structures like groins shown here on the left. These are perpendicular structures to the shoreline that trap the longshore sediment transport. And here on the right, you see beach nourishment event. That's why the shoreline is protruding into the ocean. And this area here is basically the engineered dunes that I showed before. They look small in this picture, but again, these are 7-meter high dunes, okay? So these are major nourishment events, right? And now, if you look at the trends, of demand of sand for beach nourishment practices, you see that there has been a very substantial rise in the demand of sand. And this is only for the United States, for the East Coast of the United States, for the Atlantic coast. But this trend is actually similar for the Pacific and the Gulf of Mexico. Maybe the rate of increase is not as pronounced, but it's going up, right? So it's a reasonable question to ask: is this sustainable, right? And many coastal communities might not afford or might decide not to continue to fix the landscape in place, right? And actually, we don't have to think about future events. I mean, this is happening today. Here in New Jersey, because we have had a number of nourishment events, we can have seaward growth even, not only fixing the landscape in place, but actually shoreline advancement or holding the line, fixing the shoreline in place. But in Dauphin Island in Alabama, the picture that you see here on the left, you see the evidence of overwashed flaxes here in the back portion of the barrier. So this barrier is actually migrating towards land because the nourishment events are very ephemeral. Right? So, and then in the other end of the spectrum, you have Cedar Island, which is completely undeveloped and has been migrating towards land, right? So it's important to understand if we are going to, some of these locations might transition from fully developed to something like managed retreat. It makes sense to understand how were they behaving in their undeveloped phase, right? So let's look at Long Beach Island for this, right? Long Beach Island is a barrier island in New Jersey, and it has gone through the transition over the past couple hundred years. And in order to address this question, we develop a moving boundary framework and combine that with historical maps, analysis of historical maps. Now, the cross-section, the idealized section includes geomorphic boundaries that I didn't mention before, because we include the marsh platforms too, right? So we include the back barrier marshes, the inland marshes, and therefore we include additional geomorphic boundaries like the bay shoreline, the marsh lagoon edges, and the inland marsh edge, right? I'm not going to talk about the details about the model. I would be happy to talk about that afterwards. But the key message here is that we can separate the evolution of Long Beach Island in two phases, one between 1840 and roughly the 1930s, during which all the geomorphic boundaries were migrating towards land. The ocean shoreline was retreating. You had 170 meters retreat during this time period. Overwashed flaxes were leading to the landward migration of the bay shoreline and also providing the mineral inputs needed by back barrier marshes to expand into the lagoon. Inland marshes were eroding on the lagoon side, but they were allowed to migrate towards the mainland. And this situation completely reversed during phase two, because you had a decoupling between the barrier and its associated back barrier environment. The shoreline reversed, and instead of retreating, as you might expect from sea level rise, it actually migrated towards the sea due to coastal engineering. And the marsh platforms were eroding on both sides of the lagoon, and the inland marshes, they not only didn't expand towards the mainland, but they actually lost area due to development. So how this transition, studying this transition and how the barrier was migrating prior to these human activities, I think that can be useful information. And together with interdisciplinary teams of social scientists, economists, we can come up with good guesses that include some science, right, in the decision of managed retreat or what other solutions could be the most appropriate in each case. All right, so I have only 2 more slides to conclude, right? So I presented 3 examples of how to apply the moving boundary framework over a range of time scales that hopefully illustrates the potential for this approach to provide insight on the process-based evolution of this understanding of the evolution of these systems, right? But also another point is that it could seem like this framework is very specific, but they are also versatile and portable. They can be extended. So this profile barrier evolution model, if you put a number of them connected alongshore and add some conditions for inlet development, you can have also another modeling framework that can be used to address a separate set of questions like the one here on the bottom left, led by Jaap Nienhuis. And in the case of fluvio-deltaic environments, we are accounting for additional sediment transport formulations that account for the critical threshold of motion that allows us to look at the subaqueous portion of the of the system as well. And I was joking earlier, right, about what this simulation on the right is. Well, this is to emphasize that the technique that we use, the numerical technique that we use to solve the evolution of Fluvio-deltaic environments / continental shelves and their glacial cycles is the enthalpy method and can be easily extended to 2 dimensions. Now, of course, this is not physically meaningful because it's missing the channels, right? So you would expect that at some point in the simulation, you have channels incising into the substrate, and that is still not there, but illustrates the potential to couple with some other existing models at the moment, right? And even though we cannot capture the channels, that doesn't mean that we cannot validate these 2-dimensional efforts and we are working on that, looking at connecting with flume experiments also carried out by Wonsa Kim and Tetsuji Muto. And to first order, under these conditions of sea level rise, and let me repeat the simulation, we see that we can actually capture to some degree the reduction in the width of the sedimentary prism under the sea level rise. So, but this is a work in progress at the moment. If anyone has questions about it, I would be happy to go in detail. But let me stop there, and hopefully there is some time for questions.
Okay, thanks a lot, Jorge. That was a really great talk. And yeah, we are now open for questions. So you can type in your questions, or if you want, you can ask them yourselves by unmuting yourselves. So right now, I don't see a question in the chat, but I can start. I mean, this is not really my background, but I have a very simple question. Before you began with, looking at a stratigraphic section and whether, you can actually tell sea level rise or fall just looking by a stratigraphic section, and that's where the modeling aspect comes in. Now, in case where the actual process is really complex, for example, if you have, through time, so since it's dependent on the shelf slope, and if you have that, if you have the slope decreasing through time because of sediment influx, and you have that kind of happening constantly, and that erosion, so how long can these models predict like the complexity or the dynamic change that keeps occurring with complexity of the process? Because at some point there will be sediment that is eroded from the sediment that's accumulated as well. Like you have these, like with your sea level change, you have the sediments being deposited. So it's from these sediments that, further sediment is eroded, and then you have another sort of a build-up.
And
I don't know if I'm very clear, but yeah.
Yeah, so, and we are talking about the part 1 of the talk when we were talking about this model simulation Fluvio-deltaic environments / continental shelves, right? Mm-hmm. Yeah, so you are totally right. There are so many processes that happen in natural systems that are not captured by this simulation, and that could lead to complex patterns of erosion and deposition. And one of them is river avulsions, right? So you are going to have, and for example, in Louisiana, the Mississippi River has avulsed, on average every 1,000 to 1,200 years, and has changed its path very substantially. If you are an stratigrapher and look at areas where the channel was located before, you could actually interpret some of the erosional surfaces as sea level fall potentially, but no, it's just because you had that shift, very abrupt shift in the location of where the channel was located. So those erosional surfaces was the product of water pushing the sediments down. And that's what we call autogenic or internal processes of the system that can lead to these complex processes, right? And in the case of this particular simulation, what we were looking into is something that is even more subtle and maybe even less intuitive, is that you can have changes in the relief and the curvature of the fluvial surface. And this is counterintuitive because these landscapes are by definition very mild in slope. We are talking about 10 to the -4. So you have to, in order to go down a meter, you have to walk 10,000 meters, right? So but because they are very long, we are talking about hundreds of kilometers. Subtle changes in the curvature and the relief can lead to substantial erosion in one place and deposition in some other place, right? A meter of erosion in this type of landscapes is very significant, right? So, and that is what, I guess that is what I was trying to emphasize here. But you are right, in addition to channel avulsions or the dynamics of the fluvial surface, there are many other processes that also are important. But that, I guess that the idea of this framework is let's focus on one and study whether it's important, the relative effect of this particular process. And let's purposefully remove the complexity from all others, right?
All right, thank you. Thank you so much. Are there any other questions?
I do have a question.
Yeah, go ahead.
While we're waiting for the other ones to put the comments. Thank you very much, Jorge. It was really very nice trip across the dominant timescales of analysis in the barrier systems, in the coastal systems. In part 2 and 3, especially, you were showing us some examples of interventions, natural or human interventions, that can actually affect a sediment supply, local sediment supply. I got amazed with the 10 meters per year that the cedar island can migrate towards inland. And I was wondering if how does your models that you are applying, how do they integrate this part of drastic changes in sediment supply that are relatively fast in time? How do you put it inside those models so you can have an idea about how does the barriers evolve in this case?
Yeah, so that's a great question. So these I guess that when you are talking about large changes in sediment supply, I think that perhaps you are talking about, for example, about the effect of adding the volume associated with beach nourishment, right?
Indeed.
So maybe I'm gonna go then to this slide, because if you are interested in, let's forget about the engineered views. Let's just think about nourishment. So if you have nourishment, you can do it in different ways, but one way, I'm going to annotate. If you're going to have a beach harassment event, what you're going to have is a progradation of the shoreline like this. You're going to push the shoreline, and I'm going to choose the straight line. So this could be what corresponds to a beach harassment event. Because, and to some, and you can tell me whether there is something that is missing here, but what in this model, this beach harassment event results in a seaward migration of the shoreline and a steepening of the shore face, which we see in the field. And we see that in the field, the steepening of the surface, because after a beach harassment event, you typically lose part of it. Part of it that it was deposited in the upper surface goes to the lower surface by waves. Waves are going to diffuse that profile, right? So that's one example. It looks simple, but if you add it, and then you are interested, for example, and this is something that we've done, you couple this with a cost-benefit analysis model that accounts, for example, for the relationship between beach harassment practice, beach width, and property values, for example, right? And you want to say, oh, let's define how often do we have to nourish in order to maximize property values, right? Then with this simple description of a one nourishment event, you can actually already address this type of questions and get some surprising results about, for example, the efficiency that of beach harassment practices that take into account this particular process that I was talking about. How long does it take for the sediments to go from the upper surface to the lower surface? And take that into account when you are deciding when is the next beach harassment episode going to take place. So hopefully that is one example that hopefully answers at least partially your question.
Thank you. Okay, any other comments, questions from the chat, from the audience? No?
Okay, then. So since we don't have questions at the moment, I think people can also, if they have questions later, they can go to Discord, because we have a channel there, and we have a dedicated place for Jorge's talk. So you can post your questions there, and yeah, you can interact with him even there after a few weeks. So you can later catch up on YouTube or on the same talk. All right, then. So I think we can wrap up today's session because we are up for an hour. And yeah, thank you, Jorge, for a fantastic talk. It was really nice that you could join us today and give your present your research here. And thank you everyone who's attending Landscapes Live. And we will all see you next week for the next session.